Hi there, guys. Well, welcome back. We've just done 3.0. We're now working towards doing 3P. This is a nice exercise which is coming up. This is back to some familiar algebraic territory. We're solving systems of linear equations. In other words, simultaneous equations, but we're giving them some kind of graphical meaning as well. So that's what we're up to. Just before we do that, I realized that I want to just add a little extra in about solving polynomial inequalities. We talked about solving, a cubic, essentially, ax cubed something or other is greater than 0 or is less than 0. We just talked about the shapes of those graphs. I suggested that you look at those questions by looking at when the graph is, say, for example, it's a cubic, when is it greater than 0? Well, draw the graph out, draw a sketch of the graph out, and it will help you find out the domain which works for the f of x is greater than 0. Now, I talked about cubics, but I forgot to talk about quartics and quintics as well. And, if you have a factorized form in particular, so for example, we have, I don't know, let's go x plus 1, x plus 2, x plus 3, x plus 4. Maybe that's our f of x or our y. Maybe we want to know when is that greater than 0. Now, remember that quadratics are one term and that cubics are two terms, either this way or this way. But of course, they can also just be a point of inflection if you've just got an x cubed term there, or if you've got x cubed, say, for example, plus x or plus 10. So there's graphs which will just look like an inflection like this, and don't have those extra two, extrema. Okay, but by and large, cubics have two terms, or a lot of them do, and two terms. And so for quartics, you can have a maximum of 3 terms. So either like this, an M, or like a W. Now I say a maximum of 3 terms because quartics could also look like a bit like quadratics. For example, if we just plotted y equals x to the 4, that's going to look a bit like a quadratic. So it doesn't have to have 3 terms, just like a cubic doesn't have to have 2 terms, but it's the maximum number of terms that it can have. And a lot of the graphs that we're dealing with will have the maximum number of terms. So for example, with this one here, now I know that this one is crossing through -4, -3, -2, -1. I know that those are roots. I know that this will follow a quartic shape because we've got x times x times x, giving us a quartic. And I know that a positive quartic is like this, and a negative quartic is like this. Remember that when x gets large, very large, in the positive x direction, or if the magnitude of it gets large, so in the negative x direction, that the x to the power of 4 term will dominate. So, for example, x to the power 100 to the power 4 is going to start dominating all of the other terms here, and 100 to the power 4 is obviously going to be large. So a bit like quadratics, that's a positive quadratic. This is a positive quartic. Okay, so if I was going to go through these ones here, I think it's going to go like this, it's going to go like this, it's going to go like this, it's going to go like this. Now, you might want to check those. You might want to check that. I'm pretty sure that that's the case, but you can definitely check it by putting numbers in between and checking whether they're positive or negative. Okay, so that's a quick way of solving polynomial inequalities, and that's our quartic. So for example, if we wanted greater than 0, we'd say x is less than 4 minus 4. It's between -3 and -2, and it's greater than -1. Okay, now when it comes to quartics where you've then got repeated roots, that's where it gets slightly more complicated. If I wanted to, say, for example, draw out this one, okay, x plus 2 there, and then x plus 3. Okay, that's our y again. If I want to draw this out, again, I can put in our roots, -3, -2, and -1. Now, again, this is going to be a positive quartic because we're getting a positive x to the power of 4 out of this. Likewise, if I had a 10 at the front, wouldn't change the fact that it's positive x to the power 4. So we know it's like this and not like this. By the way, it doesn't necessarily have to have symmetry between the two bumps as well. It could be that we're sort of something more like this. Okay, but the sign change we'll be able to identify from the graph anyway, so not a problem. So we know that we're going to have a repeated root here. So it's either going to go like this or it's going to go like this. So it's going to be a repeated root. It's going to touch it. And we know that it ends going up, so it should go like this. And now when we fill the rest of this in, the others are not repeated roots, so they're going to go through like this. So it's a W, but with a repeated root in this situation here. Now, when we're asking when is this greater than 0, we'd say, well, it's greater than 0 when x is less than -3, and it's greater than 0 between the two roots here, between these two here, and also when it's greater than -1. It's not actually greater than 0 when we're putting in -1. So if we change this to an equals, the answer would be easier, because we could just say, well, when x is greater than or equal to -2, because we'd include this. Okay, now just briefly into quintics as well. You can keep doing this, of course. You know, if you come up with your quintic, quintics are going to have a maximum of 4 turns. So it's going to be 1, 2, 3, 4. Is that right? 1, 2, 3, 4. Yeah, that's right. Okay. And again, it's the x to the power 5 is going to dominate overall at the end when x is large. So this would be a positive quintic, just like this would be a positive cubic. And again, you know, very similar sort of idea to drawing the other graphs. So I'm not going to bother drawing the graphs here. Again, you could have something like this would be a negative quintic. And you can carry on, of course, if you wanted a polynomial of degree 6, then it will have a maximum of 1, 2, 3, 4, 5 turns. And this would be a positive x to the power 6. Polynomial of order 6, rather, of degree 6. Okay, so that's how you might sketch these graphs out. Okay, well, there's just a little diversion there, hopefully slightly interesting. And now we're actually going to start the exercise 3P. So solving systems of linear equations, there's a nice little investigation here. It's without using a calculator, solve the following simultaneous equations. This is nice. I encourage you to have a go at this, to play around with this, to see what they're trying to push you towards, so you can think about coming up with some of this maths yourself. Okay, however, I am just going to skip through, and I'm going to skip onto this little box here. And it's talking about when you solve a set of linear equations. So we're talking about a set of equations, maybe, I don't know, x plus y equals 10, and x minus y equals 5, say, for example. Now, there we go. When you get a set of linear equations, there's 3 possible situations that could happen. One of them is that there could be a unique pair of numbers which satisfies both equations. In other words, if you draw one as a graph and another as a graph, then you'll find that it crosses at a particular xy coordinate point. Okay, that's one situation. The next situation is that there are no numbers which satisfy them. Okay, and it could be that if you were going to draw this, or it definitely will be when you draw this as 2 straight lines, we're saying, well, they never meet. There is never a point where they cross or where they overlap at any part of those 2 lines. So we're talking about 2 parallel lines would be a set of simultaneous equations which you wouldn't be able to solve together. Let's think about 2 parallel lines that say, I don't know, y equals x plus 1 and y equals x plus 2. Both parallel, they both have a gradient of 1. If we try and solve those, we could say maybe let's take away the first line from the line above. We're getting 0 equals 0 and minus 1 there. So we're getting 0 is equal to minus 1, which is clearly nonsense. Okay, so if you end up with a nonsense answer like that, then there are no numbers which satisfy these 2 equations. Right, well, the third category, by the way, this one at the top here, this one here, was of the first variety, and these two cross. Okay, and with the third one here, it's talking about there being infinitely many pairs. And that is to say, if we drew it out graphically, we'd end up having these two lines be exactly the same thing. So I don't know, let's say y equals x and 2y equals 2x. They may look like different equations, but you can see that they're the same equation essentially. Again, if if one equation is ultimately giving you the same relationship as the other one, then when you try and solve these, let's try and solve this and then take them away, then you'll end up with getting something like 0 is equal to 0. But likewise, you could end up getting something like 2 is equal to 2. As long as you're getting no particular value for x or no particular value for y, and as long as it's still consistent, it's not incorrect to say that 0 is equal to 0 there when we take this away from this, the minus there. As long as that's a consistent situation, it's just not telling us what x or y is. So that's when we've got infinitely many pairs which are going to equal to each other. Right, now that's pretty straightforward to start off with, but obviously the questions get considerably harder. That's the idea. Okay, what's the hint say? The hint says in type 3, infinitely many pairs of real numbers satisfy this system where y can be any real value whilst x is a value dependent on y. Instead of expressing y in terms of x as usual, a calculator may provide an answer where x is expressed in terms of y. Okay, so they're just talking about how a calculator might try and solve this. Okay, and of course, GDCs do solve systems of linear equations. There is an option, certainly on the TI Inspire. If you go to the normal Scratchpad place, you can solve a set of linear equations. So check that one out. Okay, but that's not going to help too much when you have questions like example 38, where you have instead of just easy coefficients which we can put in to our system of linear equations into the calculator, we can see that in this case we've actually got a parameter which we're going to need to work out here. So we can't substitute this one easily into the calculator. Right. So example 38, let's take this. And it says find the value of a real parameter m such that this system has no solution. Okay, so let's try and solve these two equations, and let's do a rearrangement of the first one. So let's call it 1, 2. So 1 can be rewritten as y equals 4x minus 1. Now let's substitute that one into 2. So explain to the examiner what's going on. Sub 1 into 2, and we can say we're getting 3 lots of x plus m lots of 4x minus 1 equals to 2. And now we're seeing that we're getting 3 plus 4m lots of x. If I multiply the brackets and factorize in a different way, and that's we've got here minus m is equal to 2. Now we can take the m to the other side, so 2 plus m. We've got divided by 3 plus 4m here, and that's what x is equal to. Now, there's going to be a lot of values of x which you can put into here, values of m, sorry, which you can put into here, which are going to give you sensible values out for x. X can be any real number. But there's only one situation here, which if you put in a value for m, that there is no solution for x. And that's a bit like thinking about how to plot our rational graphs. So when this denominator is equal to 0, there will be no defined answer here. You can't divide by 0. So m here could be any real number, but m cannot be equal to 3 plus 4m cannot be equal to 0. Now, if we solve that, we'll see that solve the inequation there, then if you take the 3 to the other side and then divide by 4, you're going to get minus 3/4. Okay, let me just check that that's the way the book has done it as well. So m is equal to minus 3/4. Now, that's not the only way of doing this question. In fact, there's quite a bit of working out there, and we may be able to make this working out less. So remember the situation. Remember what they're saying. They're saying that if you have no solutions, we've got two graphs which are parallel to each other. If we plotted these two graphs, so if we plotted this and this. So let's just think about when these two things would be parallel. So the first graph is y equals 4x minus 1. That's the rearrangement of the first one. And of the second one, we'd get my equals 2 minus 3x. And therefore, we're going to get minus 3 over mx plus 2 over m there is equal to y. So this is our second equation. Now, when these two things are parallel, then either they're going to have two lines which are on top of each other, which means that there are infinitely many solutions, or when they're parallel, they're going to have no solutions at all. So when are they parallel? Well, we know that the first gradient is definitely 4, and the second gradient is minus 3 over m. So what we could do is we could say 4 equals minus 3 over m, and so m is equal to minus 3/4 again. Now, there's another little bit here, though, in that we should just check that, in fact, when we put m is minus 3/4 in, that we are getting a different line. Because we don't actually know there if we have no solution or if we have infinitely many solutions. So we need to put m back into here and just check that we are getting out a different line to this one above. So there's another step there in order to do it by that approach. Okay, example 39, I think probably discusses a similar situation there. Yeah, there's a similar discussion as to what I've just said there after the question. Okay, 39, let's take this one. Okay, and now there's a fair bit of working out in this one. It says, consider the system of equations, and it says, find the value of the real parameter p such that the system has a unique solution. Okay, well, my suggestion at this point is just to try and find that unique solution. And they're trying to say, find the unique solution in terms of p. And so we know we've got to work towards this anyway, and hopefully somewhere in our working out, we'll realize that there will be values of p which don't give us a unique solution. Okay, so let's try and solve this thing. And I know the book makes this equal to 2px and this equal to 2px as well, by times by p and the next line by 2. For myself, I think I'd do this slightly differently. I think I'm just going to rearrange the second one. Say that's equal to, yeah, so let's just say that that one is equal to 2 minus px divided by 3. So that's your y. Okay, now what we're going to do is substitute that into the first one. Again, we really should say this is number 1, this is number 2. What's happening with number 1 now? So we're getting 2x plus p minus 1, y, got to put my equal sign in there, which is equal to 2 minus px over 3. And then that's equal to 1. So all I've done is replace my y with this expression here. There we go, there it is. Okay, so now if I multiply that out, so I've got 2x, and I might just bring the third to the front, or actually I might cheat a little bit here and just times everything by 3, because that makes it a little bit easier here. So we've got 6x plus, then we're going to multiply this by this. We're going to remember to times by our 3 on the other side as well. And so we've got, what have we got? We've got 2p and minus 2, and then we've got minus p squared x, there we go, and so that was this one times by this one here. If we do this times by this, we'll get plus px. Okay, now we can hopefully take this a little bit further. So again, we're trying to find the unique solution in terms of P. I can see that's where we're heading for. And at the moment, I can't quite see how to do this. I'm just going to take the algebra a little bit further. So let's try and solve for x here. So let's bring out, I can see I've got x involved in each of these three terms. So I've actually got 6 minus p squared plus p lots of x. And then I've got, let's take all of the other stuff to the other side. So I've got 3 plus the 2, give me the 5, and then I've got the minus 2p there as well. Now I can see I've got x is equal to 5 minus 2p over this 6 minus p squared plus p there. Now, find the values of the real parameters such that the system has a unique solution. Well, again, I think that p could be a lot of values here. Okay, so find the values. It's not necessarily a single value that we're looking for, but I can definitely see that this doesn't work when we're getting an unreal, or we're getting a non-defined answer for x. And we're going to get a non-defined answer for x when the denominator is equal to 0. So we can say that there's no solutions when 6 minus p squared plus p is equal to 0. Okay, so we've got p squared minus p minus 6 is equal to 0, and that can factorize to give us p minus 3 and p plus 2 equals to 0. So there's no solutions when p is equal to 3 and when p is equal to minus 2. In other words, p can't be equal to 3 and p can't be equal to minus 2. Now, I think p can be anything else. Let's just check with what they've got here as well. Yeah, so they're coming up with the same situation here as well. Now, when we get our situation for y, because obviously we've only done that for x, maybe when we get an expression for y here, we'll end up with a divide by something as well. And maybe it's a different factorization. I mean, I suspect that it's not, but maybe it is. But when we're looking for the unique solution, we'll definitely be able to check that our solutions for p, or in other words, the thing that makes p, this system, work with a unique solution is just all the values of p, but not these two things here. Okay, so basically what I'm saying is that we've got our value for x, and now we need our value for y. Now, and we need to check that these values are not working in the value for y as well. Okay, so y has this expression here. So we can either put in, so we're going to need to put this in for x and simplify this thing here. So for y, our other part of the unique solution xy, okay, is going to be equal to 2 minus p and then times by, we'll take out that third there actually, take out that third there, and then times by this function here for x. So we've got 5 minus 2p divided by 6 minus p squared plus p. Now we could do this in a different way if we wanted to. We could just do what we did above by, instead of rearranging for y, we could have rearranged for x. We'd probably do that from the first one and substitute it into the second one. That's perfectly fine, of course, but we're just choosing to do it this way in this case. Okay, and you can see now that I've just skipped on a little bit because doing this is pretty tedious, and I didn't have a lot of room on that page as well. So this was the last little step which I had there. Of course, you just need to simplify this. So you wouldn't leave that as your final answer. You'd take that a bit further. So you'd make sure that you have a common denominator in this case. So in other words, times the whole of this thing here by the numerator and the denominator by the denominator here. And then you can combine your two top numerators, and then you can write it as a single fraction. And then that's exactly what they've done here as well. I'm just not doing that. That's just a little exercise which you can do yourself. Okay, so there was one extra thing that I wanted to go through here, And I suppose, and that was talking about whether or not there were, if there was a possibility that there were infinitely many solutions, because we've definitely checked that this does give us a unique solution. Remember, if we have a look at their working out as well, it's exactly the same in part A. They're saying P is not equal to 3, P is not equal to -2. And you can also see that from here as well. You can see that's, by the way, just a slightly different rearrangement than what they've got. Okay, that's just my version with times in the top and bottom by -1, which makes it kind of neater, keeping things with plus p squared on the bottom. Okay, but you can see that with y as well, the solution for y, again, you can't have -2 and you can't have 3 because that will make a 0 on the bottom. Now that's partway there to saying that we haven't, that we have got a unique solution when we use -2 and when we use 3. However, does that say that we have definitely not got infinitely many solutions? Now, in other words, is there a value of p which we can put in and into, back to this, is there a value for p? Let's just take this bit here actually in part A. So is there a value for p which we can put into our original two equations, which then gives us two identical equations, just rearrangements of each other? In other words, if you do that, you'll end up going down your lines of algebra and getting something like 0 equals to 0. That will give you infinitely many solutions. Like when I said 2x equals to 2y and x equals to y, when you double this line and take them away from each other, you're going to get 0 is equal to 0 there. Now, here's the case where you would get no y's equal to nothing. That's this case here. Now, the only case in which that's possible is when p is equal to 4. When p is equal to 4, we can see that you're going to get 4 squared minus 4 minus 6 on this side here. So you're getting 16, take away the 6 is 10, take away the 4 is 6. So what you're getting from that situation there, if it's possible to get a 0 on the right-hand side, well, it's not possible to get a 0 on the left-hand side. So in other words, when you put in p is 4, then you're going to get 6y is equal to 0. Now that's not going to make any sense at all. So in other words, there isn't a value of p where we can get 0 is equal to 0 in our working out. Another way to have checked that would have been to have created a 0 there and checked that you don't get a 0 on this side. So by putting in 3 in here, you get a 0 on this side, but obviously that doesn't give you a 0 on this side. And by putting in p as -2 in here, we get a 0 here. But again, we're not getting a 0 here as well. So we've just checked the case that we don't have infinitely many solutions. And I think that the book doesn't check that. That leads us up to 3P. The exercise 3P has 4 questions there. These are really good algebraic questions to be doing. Now we have only 2 exercises after this until we finish the end of this exercise. Thank you for listening in today, guys. Good luck with the exercise, and I'll see you for the next one.